Hi, everyone. Thanks for coming. My name's Ellie. I work at Uber San Francisco. I'm an iOS developer in the mobile platform team. In this talk, I'll be going over the development aspect of code generation for Swift with a focus on mock generation. The clicker is not working. 1 second. There we go. So what is code generation for? It's useful when you have a large amount of boilerplate code you don't want to write by hand. For example, if you're using a certain design pattern or an architecture, you might have to write multiple components to fit certain requirements of the architecture. And that might require some amount of boilerplate. Or if you're writing model objects for your app and you need thousands of them, writing them all by hand can be very tedious. Or if you're writing mocks for your unit tests and you need hundreds of them, writing them all by hand can be very repetitive. This is when code generation can become very useful. You can automate all the generation and focus on other important things. So now the question is, can we build one? Is it complicated? Do we have to modify the compiler or use multiple frameworks? The answer is no. You can build one using a minimal set of frameworks. In fact, if you want to build one that's performant, keeping things lean and simple is the key. At Uber, we have a very large code base. We have over 2 million lines of code. We have several apps, one for drivers, one for riders, one for bikes and scooters. Then there's Uber Eats and Uber Freight, and so on. And they consist of about 350 modules. We have very complicated dependencies among all these modules. And we are using a design pattern that allows nice separation, but is also template heavy. So we built multiple code generation tools, such as dependency injection automator, called Needle, which is open sourced. We also built model generator, resource generator, mock generator, and so on. I'd like to dive into one in particular, mock generation. So why do we need to do this for Swift? Swift is a static language, so it comes with enhanced type safety and security, which is great. But that also means the runtime access is very limited. It's read-only, unlike Objective-C. So that makes mocking very difficult. So then you might ask, why not use the OC mock with Swift? Well, then you'll have to subclass NS object and an add opc attribute to all the override methods. You can't have generics, and you can't mock class methods, and so on. So in practice, the answer is no, it's not recommended. Then you might ask, what about something like Swift annotation? Well, there's actually a pitch for that. And there's a long discussion going on in the Swift forum. And I think it's possible that Swift compiler team may add support for that, but it'll take a while until that happens. So what about other mocking frameworks for Swift? Why not just use those? So we actually ran a few, such as Sorcery and Cuckoo. And we ran them on our code base, and we found that the numbers were not quite scalable for us. We have over 2 million lines of code and about 11,000 protocols. And we needed to generate about 9,000 mocks, which were about 500,000 lines of code. They took about an hour longer, and even with caching enabled, took several minutes. And in some cases, caching wasn't even an option. We wanted something much faster, fast enough that we can integrate it into our build system. Ideally, we wanted something faster than 10 seconds. So we decided to build one on our own. So how do we go about building one? And more importantly, how do we go about building one that's performant? There are a few things to consider before you start building a tool like this. How can I parse source files? Can I use existing parsers? What are the pros and cons of each? And what's suitable for my tool? Should I mock protocols or classes or both? What annotation should I use? Should I support something like namespacing in case of name collisions? How about resolving inheritance? Is there something clever I can do? What template system should I use for the mock output? And what can I do to make it performant? Let's start by figuring out what our goal is. How do we identify types to mock? And what should the output look like? We chose to use an annotation called @mockable. This follows the syntax of the built-in annotations, such as @available and @offc. For types to mock, we chose protocols for the time being, because it's simpler to implement reliably. But support for mocking classes will be added in the future as well. Now, what should the output look like? Given protocol foo, we need a class called foo mock. We need an initializer and a call count variable to keep track of the function call counts, an underlying function handler, and the function that sets the call count variable and uses the handler inside the function body. And we need to think about the end-to-end process. First, we need to parse files, then perform type and annotation checks on the ASTs, and get a list of candidate protocol entities along with their metadata. Then we resolve inheritance and generate a set of unique models, which will then be rendered with templates. Then we have the final output, and we can save that to a file. Let's take a look at each one more closely, starting with the parser. There are two choices Apple provides, Swift syntax and SourceKit. We chose SourceKit because it's a lot faster. Parsing takes about 1 to 2 milliseconds, whereas Swift syntax is about 20 times slower. There's a lot more overhead in Swift syntax. It launches the Swift C process per file, whereas the SourceKit daemon keeps running after it's launched. Sometimes you need extensive type info in cases like name collisions. Swift syntax doesn't provide any, whereas SourceKit provides an API for that. We are using the SourceKit framework, which is a thin wrapper around SourceKit. This is the only third-party framework we are using. This provides nice and convenient APIs to look up the annotations and declaration types. Given the ASTs from parsing, we now filter them with type and annotation checks, and we get a list of candidate protocol entities along with their metadata. Note that we also gather the import lines at this time. Getting the precise modules to import takes a lot of analysis, and it can take a long time. And there's no efficient tool for that right now without involving the compiler. So for the time being, we're simply collecting the import lines from the source files we parse. We can multi-thread this step for faster performance. Since we have over 2 million lines of code, we knew parsing would take a long time. So we added an option to multi-thread this step. When it comes to concurrency, there are different ways to implement it. One way is to simply use the built-in GCD. This, in general, maximizes concurrency. But maximizing concurrency isn't always the best option. Too many threads can actually hurt performance. Threads can fight for cache, evicting each other's cache data, and cause memory thrashing. In an extreme case where you have hundreds of threads are running concurrently, the overhead of saving and restoring registers and cache states between suspending and resuming threads can all add up. In our case, we had an even worse problem. When too many threads try to access the SourceKit daemon, it caused the daemon to hang. And this happened on CI, so everybody freaked out and tried to figure out different ways to solve it. We tried different methods, but none of them worked reliably. And even restarting didn't actually fix the problem. We found that the only viable option was really just limiting the concurrency. So we tried to do that, and we thought there should be an API where we can set the limit directly with a dispatch queue. But there wasn't one. Instead, we had to use a dispatch semaphore. You can pass in the limit to its initializer, and we found that setting the limit to the number of cores was a reasonable solution. To gain a finer control over concurrency, we can break down the work into smaller tasks. We can then group them and chain them in a certain order. To do that, we need a task and a task handler. Task has an initializer, which takes in a closure with a handler and a result parameter. Task handler has its own dispatch queue and finish and fail function. In task, we can write a small routine, such as parsing and checking for type and annotations. And if it's successful, call the handler finish with results. And if not, call fail with an error. This routine will run when the perform function is called, which dispatches this task handler asynchronously. We can group these tasks to run concurrently and wait for all of them to finish at the same time using dispatch group. We can also chain them in a certain order by iterating through them and calling the perform operation on each. Once we built all these abstractions, we can then chain them nicely, as shown on this slide. This makes code a lot more clear and a lot more readable. Now that we're done with the parsing task, we can move on to the next step, resolving inheritance. Here we have protocol foo, which inherits bar, which inherits baz. To resolve inheritance, we can simply walk up the tree and generate models for each corresponding protocol. That's great. But what if you have cases like this, where you have multiple parent protocols and multi-level inheritance? Now you need to walk up the tree repeatedly. One obvious way to optimize this is to cache the results of the walks so the subsequent visits are cheap. Okay, but can we do better? Of course. Here's another approach we came up with. In this case, in the same hierarchy, say bar and baz and their dependencies are in a different module. Instead of walking up the entire tree like before, we now simply look up the output of bar. This output contains mock classes of bar and all of its parent protocols in that module. And now we can just look up those entries in that output and skip walking up the tree entirely. This requires dependencies to be pre-computed and pre-compiled. But since the build system already has this info, and we want you to run this tool during the builds, this approach actually worked quite well for us. During this step, we're also generating models. We generate them lazily for performance reasons. In this example, we create a function model for a function visit, which contains the name of the function, the return type, the access level, and the parameter list, and so on. This references a list of parameter models, which contain the name, label, type, etc. We also create another model for the function handler, which is an underlying closure variable used inside the function body. When you're generating models, there are a few things to keep in mind. You want to make sure each model is associated with a unique identifier, so there's no collision. As in this example, overloading allows functions to have the same name, but different types. But the underlying variables have the same type. So we need a way to differentiate them, and we do that by using unique identifiers. In this case, we have several functions called visit, but with different types. The underlying call count variables should all have different names. Sometimes the same signature can satisfy multiple protocol requirements. In this case, we have protocol foo, which inherits var, and it has an overloaded function called visit with the same type int. And we only need one underlying variable in this case. This issue comes up again in the initializer for variables. In this case, we have an overloaded var called coffee. In the mock class initializer, we need one parameter for the variable coffee. After filtering out duplicates and uniquifying these models, we are now ready for the next step, rendering. There's a template library called Stencil, and it's used by a lot of open source projects. So we looked into that as well. But when we benchmarked it, we found that it took more than 1 minute for our code base. Remember that our goal was maximum 10 seconds in total. So we compared it with simple string interpolation, and it was much faster. So we chose that method. And we were still able to achieve templating using multi-line literals and custom string interpolation without using the library. When writing output contents, it's important to keep in mind the developer experience. For example, here we have function f, which returns type int. In the mock output, we first check to see if there is a handler, and if so, we call that handler. If not, we can either call fatal error or provide a default return value. If we provide a default return value, users don't have to write the handler for each function. And that's a lot more convenient. We provide default values for tuples as well, but this creates challenges of its own. The first two examples on this slide are pretty straightforward. But the last one contains nested tuples, and we need to make sure we parse them correctly so we can provide a default value for each component. It gets more tricky if you combine those nested tuples with collections. In the first example, we can just return an instance of array, and in the second one, an instance of dictionary. But in the third one, we need to return a tuple of int and dictionary. The default value for that is a tuple of 0 and an instance of dictionary. Then in the fourth one, we need to return a tuple of int and a nested tuple of double and dictionary. For the default value, we need to return a tuple of 0 and a nested tuple of 0.0 and an instance of that dictionary. But in the last example, since this is an array of tuples, we now simply return an instance of that array without having to parse the tuple element. As you can see, it can kind of get out of control. It would be nice if SourceKit gave us an AST tray for return types like this, so we don't have to parse them by hand. But all we get is a long string, and it's up to us to break it down and parse it correctly. There are tools like a parser combinator for things like this, but it has performance implications, so we decided to build our own custom parser. Putting all these pieces together, we now have the final mock output. We have import lines, we handle attributes correctly, we have a class and an initializer, we have functions and variables and the underlying variables, and so on. And now it's ready for use. Okay then, we're done now, right? Can we go home? Well, I wish. It's not over yet. There's a little more left to do. It's profiling time. We need to make sure we are not doing anything crazy. It's important to profile not just what you wrote, but also commonly used APIs. Just because you're using a standard library API doesn't mean you can blindly use it and assume that it'll be performant. There's a lot going on under the hood that you might not know about. Benchmarking equivalent functions can sometimes yield surprising results. We found that some functions are slower than others in the standard library. And by replacing them with faster ones, we gained up to 300 times speed up. For example, the string split function takes about twice as long as the components separated by. And if you already know what encoding you're using for all of your strings, it's better to specify the encoding when you call a string API. That can save you a lot of time. Besides strings, the URL initialization with file path can also be expensive. It performs a file operation to check if a file exists at the given URL path. You can pass in a flag to its secondary argument, isDirectory, and that'll skip that operation, and it can speed things up. And typecasting is expensive, so if you can use an enum or a variable to identify certain types and filter them, it can be a lot faster. After profiling and tuning, we benchmarked our tool and compared the results with other frameworks. The result was about 5 seconds, multi-threaded, and it was much faster than other tools. This was also faster than our initial goal, so we were happy with the results. We also ran it non-multi-threaded, and even then, it only added about 12 seconds extra. Because it was very fast, we were able to integrate it into our build system. And this is only with a minimal amount of optimizations. And we're not even using caching. So there is plenty of room for further improvements. Okay, with that, now we're done. Are you ready for recap? Let's recap. Let's go over how we made the tool performant. We leveraged concurrency. We filtered unnecessary types or files. We generated models lazily. We pre-computed dependencies where applicable. And profiled standard library APIs that were commonly used. We used string interpolation instead of stencil. And we kept dependencies on third-party frameworks to minimum. This way, it's easier to debug, profile, and keep track of things. The tool will be open sourced in June. It's called Mockolo, and it'll be on GitHub/Uber. It has Swift package manager support, and you can use the tool as a command line. I'll be making an announcement when it becomes public, so stay tuned for my tweet. Hopefully, this talk gave you a motivation to build your own tool. Everything I covered today can be applicable to other code generation tools. If you're building one, remember to keep things lean and performant. Also, try out Mockolo when it's out. And if you have feedback or if you want to contribute to the open source development, it'll be greatly appreciated. That's the end of my talk. Thanks for coming. Hope you enjoyed the talk. I can take questions now.
First of all, thanks for your great talk. The last time I tried to use SourceKit to extract stuff from the AST, I had the issue of SourceKit basically, or rather SourceKit, omitting any kind of information regarding generics. Did you have the same issue? And if yes, how did you resolve this?
What do you mean by, like, what problem did you have when you were trying to extract the generics?
If you have like a struct foo generic over T, then the generic over T part was just missing completely from the output of the structure command of SourceKit.
So you're saying that it didn't even show T, or are you saying that you were expecting some substructure and then that was gone?
The output was equivalent to if you just had struct foo, basically.
I see. So what we saw was just a long string that captures, for example, the bracket T bracket. It showed all of that, but it didn't show any substructures. So for example, if you have function with a generic bracket T bracket and the arguments, it did show the generic part, the type parameter, but it didn't show up as a substructure. But we still saw it as a string format. So that kind of goes back to what I was saying earlier. It would be nice if SourceKit gave us an AST tree instead of just a long string. And this is the problem where we had, in terms of like tuple parsing and whatnot, if we get those, the AST tree with all the substructures, that are laid out nicely, then we don't have to do the parsing ourselves, right? So that's a limitation with the SourceKit, I believe, yeah. Any other question?
Hi, thank you for the great talk. Personally, I was very surprised how the great attention to detail at Uber is. I have seen also your talk putting your app on diet, which was very detailed. And I would like to know how does the benchmarking process go at Uber? I've seen different values, so I would be curious how is benchmarking done at Uber?
Are you asking about how we benchmarked tools? And
yeah, for this talk, for example, yeah, what were the criteria and how did the tests go in order to reach that values?
So we started out by benchmarking well-known tools because we thought that we can just use a third-party framework instead of building one. And we simply ran it on our code base, and it was taking a very long time. So then we simply started the Apple instruments, and we looked into what was the bottleneck. So we found the bottlenecks of each framework, and we thought that, okay, we can either try to go in and fix those things, but then there were other problems as well. So we thought it would be simpler if we just build our own tool. And as we were building our own tool, we also benchmarked our tool to make sure that we are not doing anything crazy. And the profiling process, it was actually an iterative process. It wasn't just done at the very end. As we were building the tool, we kept profiling and making sure that everything's efficient. Does that answer your question, or was there a follow-up question?
Yeah, and that 10 seconds as a target was for one project or for all projects? I mean, what was the goal, this 10 seconds?
Right, so the reason we had the 10 seconds goal was because we wanted to integrate the tool into our build system. So during the build, it generates the mocks so that we don't have to. So initially, we're thinking, maybe we can just run this tool during the linting step. So maybe it can take a little bit longer than 10 seconds. It could be maybe 20 seconds or whatever. But that means that every time you push your PR, it runs the linting step, and that adds another 20 seconds, and we didn't want that. So we really wanted to optimize this and bring the number down so that even when you're running it as a separate linting step, it's super fast. And even better, if we can put this thing in the build system, it's a lot more efficient. You don't have to run anything manually, or you don't have to introduce an extra step when you're pushing your PR. So that's why we wanted to have some sort of a threshold we can tolerate when we are running this tool during the builds. And so that's the number we came up with, 10 seconds.
Okay, thank you very much.
Mm-hmm.
Hello? Hi.
Yeah.
Hi. So on the Profile APIs slide, you showed lots of effectively non-trivial differences between performances. I'd like to know if Apple have themselves a series of functions to tell you the relative efficiencies, and if not, when you release Mockito, would you be, sorry, however you pronounce it?
Mockolo.
Mockolo.
Yeah.
Sounds like a wonderful drink.
They're all similar names, yes.
Yeah, wonderful. Would you be able to also release all the performance rates and profile efficiencies associated with the standard libraries? Because it seems fairly interesting to know.
I hope that they know that certain functions are slower than the others. I'm not sure what their priorities are in terms of optimizing certain functions to make it a lot faster. I know they have a lot, on their plate, but yes, it'll be a great idea to release these numbers, so maybe we can get Apple's attention and they can work on optimizing it. And I'll put that on the to-do list. Okay. Any other question?
Hey, thanks for the great talk. So having some experience with Swift compiler, I wanted to ask, so how long then it takes to compile this 500,000 lines of Swift code, mocks?
So compiling mocks, okay, so let me tell you that compiling the whole project takes about 15 minutes. And mocks portion is about a quarter of that, because we have over 2 million lines of code. And the mocks portion is about 0.5 million lines of code. So it's a quarter of that, but this is not run during the release build. This only runs during the debug build. And so the quarter portion of that is theoretically spent on the mocks. We haven't profiled the build time for the mocks itself, but that's what we're going to do next, since you're asking the question. Thank you. Yes.
Hi, good job. Did you try the Swift syntax that is on the branch master, and it will be released with a Swift point.1 about the time when you release this project? It is significantly faster. Did you try it?
The latest master, no. When we tried the Swift syntax, this was about 3 months ago. So it's not too latest, but it's still not too old. Yeah. And so can you actually tell me, on the latest master, does it launch the Swift C process profile or no?
Well, the version on the master basically linked this new library lib Swift syntax, yeah, and it used directly parser from the Swift Clang version.
I see, so it doesn't launch Swift C process profile anymore.
It's not, it is significantly faster.
Do you happen to have maybe some numbers in your mind?
I don't have on my hand, but you will find it on the forum, Swift forum. Okay. Swift source group or something.
So maybe that will help with performance. What about extensive type info? If I want to get the whole USR, can I get it with Swift syntax?
Yeah, you would need to parse everything, but that does make another question. Did you play with the index?
With the what?
With the index.
With the indexing?
Yeah.
Yeah, so that's another thing we could look into. After it's indexing, we can call the API and it'll make things a lot faster. but we still have to wait until the indexing is done, etc. And if the indexing gets hung or breaks in the middle, then we have to restart, etc. So it also kind of brings in a few other problems as well. But that is also something we're going to look into. Thanks for bringing that up.
Another thing is with this SourceKit stuff. You mentioned that there's an issue with the concurrency, right? Did you try actually load the SourceKit as a library, or it was as a XPC process?
So it actually uses the in-process SourceKit library, but that eventually launches the XPC, the daemon, the auto process daemon, and then it keeps hitting that. So there is no other way around that.
Okay.
Yeah.
Hi, thanks.
Yeah. I see a few hands. Can you put microphone?
Hi.
Yeah.
Thank you for a great presentation.
Thanks.
I used one mocking framework. I think that it was Sorcery, and I didn't like this framework because I have, for example, 10 protocols, not 1 million, but 10, and I needed to create exact source path for each protocol, and I needed to define output file for each of that protocol. And let's say, for example, that I have 10 protocols in one group and 10 protocols in another group, and these two groups is inside another group. And with your framework, is it possible to, let's say, I want to use all of the protocols in this group with one output file?
Are you saying that in Sorcery you were having a trouble with parsing all those protocols and outputting to one file?
No. For me, it was a problem to define source path for each of protocols. So I just wanted to define one source path for one group, and I wanted to define one source path for one group and one output, so I can get 10 mock.
When you say group, what do you mean exactly? You mean in a module?
Folder.
In a folder?
Yeah.
So does that folder map to a module or just a directory inside a module?
It's directory inside a module.
But there are other directories for that module as well?
Yeah.
Okay. So you're saying that, oh, I see. So you're saying, okay. So you want to group all those protocols inside the directory and output those into one file for that directory.
Yeah.
But with Sorcery, it didn't let you do that because everything gets combined into one output. So that includes other directory protocols as well.
Yeah.
Okay. That one's pretty easy to configure. You might have to modify the Sorcery output portion code. But if you go into the Sorcery code, if you clone the Sorcery, and if you find the portion where they handle the output portion, you can either pass in a list of output file paths, or you can modify the source code to generate them by hard coding. You can configure that pretty easily. Yeah.
Okay, thank you.
Any other question, or are we out of time? We're out of time. Okay, I'll be around, so if you have more questions, come talk to me after. And thank you, everyone.